All right, so this is the first example that we're going to do, and this is pretty much as complex as this gets, to be honest with you. So if we look at the buckling equation, if I go back right here, this P critical equals pi squared EI over KL squared. If you think about it, E has to be given unless the sort of problem is to identify a material to be used. I either has to be given or solved for. KL has to either be given or solved for. And P critical has to either be given or solved for. So in general, the process of these problems are, given an EI KL, what is P critical? Or given P critical and KL, what is the required I? And so forth and so on, right? So we would have to give you, all of the parameters except for one, and then you would simply use this expression to solve for the one that was not given, right? So in this particular case, we have, and this, by the way, is a problem that is definitely on the FE exam. Every FE exam I've ever seen has some sort of variation of this problem on it, right? So we've got a weak axis and a strong axis, right? And the weak axis is about this axis, right? So that is the weak axis. And then the strong axis, I guess I'll do it in green here, is somewhere like sort of right here, right? So the green is the strong axis, and the red is the weak axis here. Sorry about that. Stupid phone is buzzing. Okay, so the column oriented sort of perpendicular to the weak axis, right, has an extra support here, right? So the buckling load of that column for the weak axis looks like this. It looks something like that, right? And then the column oriented perpendicular to the strong axis, right? So the cross section has a lot more moment of inertia in this area. So I don't need as many supports, right? And that is going to look something like this, right? So for the strong axis, right, K is going to be 0.5 because it's fixed. But the overall length, right, is going to be 20 feet. And for the weak axis, K is going to be 0.7, but the overall length is just going to be 10 feet, right? Because I'm going to say that it buckles. So if we do this in red, right, I'm going to say that it buckles across this area here, right? So this guy is 0.7 times L over 2, right? Where L is 20 feet, right? And this guy here, right? And this guy here is 0.5 times L, right, which is 20 feet, okay? L being 20 feet, obviously 0.5 times L is 10 feet. So we're going to try to do this problem. Basically, the question is, what is the buckling load? And the complexity of this problem is you don't know which direction governs, right? Is it going to buckle in the weak axis, right, even though I have more support, right? So my KL term is much smaller. Or is it going to buckle in the strong axis, right? I have less support, my KL term is much larger, right? But my moment of inertia is much larger as well, right? So just by inspection, as they say, it's sort of impossible to figure out which direction this is going to buckle. So we just have to solve for both, and then whatever is the lowest buckling load, that's the one that governs, right? We're solving for a capacity here, so the lowest capacity governs, right? So if I start with the weak axis here, right? So I'm going to call it IW for weak axis, right? This is BH cubed over 12, right? In this case, the B is 6, or sorry, the B is 16. The H is 6. I divide that by 12, and that equals 288 inches to the fourth, okay? And then I'll get my KL in the weak axis, right? And that is just 0.7 times 0.5 times 20 feet, right? And so that ends up being, and in fact, you know what I need to do here? I also need to multiply this by 12 inches per 1 foot. So this ends up being 84 inches. So one of the keys with this is just keeping your units straight. So if the length units are in terms of inches, then all of the units, all the length units have to be in terms of inches as well, right? So P critical here for the weak axis is just pi squared times E, 10,000 KSI, times I, which in this case is 288 inches to the fourth. And that is all divided by my KL, which is 84 inches squared. Right? And when you work that out, you're going to get 4,028 kips. Right? Something like that. Right? Hopefully that makes some sort of sense, right? So if we move on to the strong axis now, so we're going to do the same thing, but everything is going to be in green, and it's going to have a little s as the subscript, right? So this again is just BH cubed over 12, right? Notice I could give you a stranger cross section, and you just use parallel axis theorem to solve for it, right? I could give you a cross section that has multiple materials, right? And you would just transform one of the materials and solve for the equivalent EI, right? And then use that for buckling. So in this case, my B is 6, my H is 16, right? And so my I in the strong axis is 2,048 inches to the fourth, okay? And then my KL in the strong axis is just 0.5 times 20 feet times 12 inches per foot, right? And that ends up being 120 inches, okay? So now I can solve for my P critical, right, which is just pi squared, 10,000 KSI. Right? I noticed a number of you on the exam didn't like the KSI there, or didn't notice it, I should say, switched kips into pounds, but then left the KSI when it came to E. And that, of course, screws up everything, right? And that's why you ended up being off by 3 orders of magnitude. All right, so then this becomes 2048 inches to the fourth, and that is now all over 120 inches squared, and that is 14,036 kips. All right? So the solution to this is that P critical actually equals P critical in the weak axes, right? Which was 4,028 kips, right? And this is going to buckle in weak axis. Ooh. this right here is the solution to the problem, right? You needed to check both, right? So I've got 14,000 kips in the strong axis, and I had 4,000 kips in the weak axis, right? Since 4,000 kips is less, that's all this column can take, right? Now, what could I do, right? How could I change it, right? Well, maybe I could redesign the column a little bit, right? If I don't want to increase the cross-sectional area, I could make the width, say 8 inches and the height 14 inches, right? And see if I couldn't get, a little bit more balance in both directions, right? This is very imbalanced. In one direction, I get only 4,000 kips. In the other direction, I get 3.5 times that, right? But I can never make use of all of this capacity, because it's always going to buckle in the weak axis first, right? The other thing I just wanted to mention quickly is that just because I use weak and strong axis, that does not mean that the weak axis will always govern, right? Because I've got different boundary conditions here in the weak axis, right? So inherently it has, it's going to have a higher buckling load. So if I look at, for example, this 288 versus this, 2048, right? You would think that the strong axis should have 10 times the buckling capacity, right? But it doesn't. It doesn't, because this has a denominator of 120 squared, where this guy here has a denominator of 84 squared. So it's a much smaller denominator, right? Again, by inspection, it's very difficult to understand, what is actually going to govern. So you do have to calculate both. And just changing a few dimensions here or there, or boundary conditions, I can easily make the strong axis govern, right?